All right, today we're going to continue talking about radicals and rational exponents. All right, so we're going to talk about, yesterday we did multiplying and dividing. Today we're going to talk about adding and subtracting. Adding and subtracting, you can only combine them if they have the same radicand, which means the inside has to be identical. If the insides and the indexes, I should say that too. In other words, you can't do a square root and a cube root, but if the indexes and the radicands match, you have what we call like radicals. And when you do that, it's just like saying, what is 7x plus 6x? Well, you would say it's 13x. Well, all you're doing is saying 7 square roots of 11 plus 6 square roots of 11. That makes 13 square roots of 11. Treat the radical just like you would any a variable. And if they match, then it's the same variable. The book does all this distributive property stuff. And so you see what they did? They said factoring, all right? They said that they could factor out a square root of 11, which they haven't taught you factoring yet, so how you would understand this is beyond me. But they do it like this. They factor out the square root of 11 and say, if I factored out the square root of 11, 7 plus 6 would be left. And then you would add those, which would give you 13 square roots of 11. All right, I don't do the whole distributing it out. It's not necessary. All right, so again, it's just like adding x's. All right, so it says add or subtract as indicated. As long as the radicands and the indexes match, you keep that and just add the coefficients. 7 plus 5 is 12. These match, so keep that and do the coefficients. 1 minus 7 is negative 6. Okay, what if they don't match? Well, then you can't add, or can you? Dun, dun, dun. Remember how we simplified radicals. I can't simplify this because 3 is a prime number. But 12, if I break it down, by 2 is 6, by 2 is 3. That's a 4, square root of 4 is 2, so this is going to be 2 square roots of 3. Now they match, so keep it and add coefficients. 7 plus 2 is 9. Okay, these do not match, so I need to break them down. If I break down 50, by 2 is 25, by 5 is 5. Bundle of 5 makes 25, square root of 25 is 5. He doesn't have a pair. Now, there's already a 4 out here, so I've got this 4 times this 5 times that 2 and that x. You still have an x in there, so this becomes this, which is now 20 square roots of 2x. If I break down 32, by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2. That's 4, square root of 4 is 2. That's 4, square root of 4 is 2. He doesn't have a partner. So I have a negative 6 times a 2 times a 2 times a square root of 2 times a square root of x. Because that x up there. So that gives me negative 6 times 2 is negative 12 times 2 is negative 24 square roots of 2x. And now these match, so I can keep it, and 20 minus 24 is negative 4. Okay? Alright, so you try this one, hit pause, come back when you're ready. And hopefully you got 3. These match, so I keep the square root of 2 and do the other math. 8 minus 4 is 4. Try this one, hit pause, come back when you're ready. Alright, I got to break these down. If I break down 8, by 2 is 4, by 2 is 2. That's a 4, square root of 4 is 2. And this one's in. So I've got my 10 times my 2 times the square root of 2. 200, switch colors. Oh, so this gives me 20 square roots of 2. If we work on the middle one, if I break down 200, by 2 is 100, by 2 is 50, by 2 is 25, by 5 is 5. So I've got a pair of 2's, which makes 4. Square root of 4 is 2. A pair of 5's make 25. Square root of 25 is 5, and he has to go back in. So I have a negative 4 times a 2 times a 5 times the square root of 2, which gives me negative 40 square roots of 2. And the one on the end, 98, break it down. By 2 is 49, by 7 is 7. A pair of 7's make 49. The square root of 49 is 7. 2's back in. So I have a minus 8 times my 7 times the square root of 2, which is negative 56 square roots of 2. And now, do you see that all of the radicals match? So I just do keep that, and I do 20 minus 40 minus 56, and I get negative 76. All right, try this one. Hit pause. Come back when you're ready. And hopefully you got 1. Okay? If I try to break down 6, I get a 2 and a 3. There's not 2 of anything, so this one's prime. I can't do anything. The middle one, if I break down 24, by 2 is 12, by 2 is 6, by 2 is 3. I got a pair of 2's, which makes 4. Square root of 4 is 2, and those are back in. So I have a negative 2 times my 2 times the square root of 6, 2 times 3 is 6, times x, which makes negative 4 square roots of 6x. And then my one on the end, 150, I'm going to go by 2's, 75, by 3, 25, by 5 is 5. I got a bundle of 5's. 25, square root of 25 is 5. Those are back in. So I have negative 7 times 5 times those two are back in times square root of x, because x didn't have the power to get out. So that's negative 35 square roots of 6x. So now I can keep the square root of 6x and just do 1 minus 4 minus 35, and I get negative 38 square roots of 6x. Alright, so how do you add and subtract radical expressions? You have to make radicands match and then add or subtract coefficients, numbers in front. Okay? Alright, so we're going to talk about rationalizing a denominator. The calculator screen in figure P11 shows the approximate values for this and for this. And they literally just typed in 1 divided by the square root of 3 and got this. Then they typed in the square root of 3 divided by 3 and got this. They got the same answer from 2 different math problems. What? What they're doing is they're saying, somebody a long time ago, I don't know who, but if I ever found him, I'd like to kill him. Because they just made up dumb rules that said, you can't leave a radical in the denominator. Why? I don't know. I just don't like it. I have no idea why. Maybe there is a good reason. I don't know. I think it's just to make us do extra work. So what they do to rationalize it means you can't leave a denominator in the, you can't leave a radical in the denominator. So we rationalize it by basically multiplying it by itself or its conjugate if it's a binomial. But if it's just a monomial, you multiply it by itself, which is legal as long as whatever you do to the bottom, you do to the top. On top, 1 times the square root of 3 is the square root of 3. On bottom, the square root of 3 times the square root of 3 is the square root of 9, which is just 3. And that's where these are equivalent values. It's just like reducing 2/4 to 1/2. We're not really reducing, but we're getting it, rid of the radical in the denominator. All right. Alright, this process involves rewriting a radical expression as an equivalent expression in which the denominator no longer contains any radicals. The process is called rationalizing the denominator. If the denominator consists of the square root of a natural number that is not a perfect square, you're going to multiply the numerator and the denominator by the smallest number that produces the square root of a perfect square in the denominator. Alright, so if we look at this, they want us to rationalize the denominator. So I'm going to multiply by the square root of 6. And I don't have my calculator, so hold on, let me get to this page. So I've got 15 over the square root of 6. On top, that's going to give me 15 times the square root of 6. And on bottom, that's just going to be 6. And it's rationalized, but be careful. If you can reduce the outside numbers only, do not touch the inside radicand. You can't reduce inside a radical. But the 15 and the 6 can be reduced by 3. So if I divide them by 3, I get 5 square roots of 6 over 2. We still have a radical, but it's in the numerator, and I don't care about the numerator, it just can't be in the denominator. So for b, I'm going to multiply it by the square root of 8. And that business that they were talking about, the smallest number that produces the square root of a perfect square, I don't bother with that. It all reduces down in the end. Well, sometimes I do, sometimes I don't. If it's not very big, I don't bother. So on top, I would have, well, you know what? Maybe I should, because you're going to have to reduce anyway. All right, let's reduce that radical first. So if I break down 8, by 2 is 4, by 2 is 2. That's 4, square root of 4 is 2, so I can rewrite square root of 8 as 2 square roots of 2. So now, to rationalize, I don't need to multiply by the square root of 8, I just need to multiply by the square root of 2. That gives me 12 square roots of 2 over 2 times 2, because the square root of 2 times the square root of 2 is the square root of 2 squared, which is 2. And 2 times 2 is 4. So that gives me 12 square roots of 2 over 4. Divide the outside only, and I get 3 square roots of 2. Okay? Alright, on this one, I'm going to break down 18. By 2 is 9, by 3 is 3. Pair of 3's make 9, square root of 9 is 3, he's back in. So I have the square root of 5 over 3 square roots of 2. Okay, so now to rationalize, I got to multiply by the radical on the bottom. So square root of 2, square root of 2. That gives me the square root of 10 over 3 times 2, which gives me the square root of 10 over 6. And no, you can't reduce the 6 and the 10. Okay. Alright, you try one, hit pause, come back when you're ready. And hopefully you got square root of 5. So if I rationalize this, I can't simplify the square root of 5. I'm going to multiply the top and the bottom by the square root of 5. On top, I get 5 square roots of 5, and on bottom, I get 5. They cancel, and I just end up with the square root of 5. Okay, try this one, hit pause, come back when you're ready. And hopefully you got 4. Alright, 3 is prime. I can't factor it or simplify that, so I'm going to multiply it by itself, but I got to do it to the top. On top, that gives me the square root of 21. On bottom, that gives me the square root of 9, which is just 3. Okay? Give me just a second. Alright, I'm back. Yeah. Alright, so when do you need to rationalize a denominator? If there is a radical in the denominator. How do you rationalize a denominator? You multiply by the radical if it's a monomial. Okay? All right, so radical expressions that involve the sum and difference of the same two terms are called conjugates. Conjugates are used to rationalize denominators because the product of such a pair contains no radicals. If I take the square root of a plus b, square root of a plus the square root of b, and I multiply it by its conjugate, square root of a minus square root of b, this would be the square root of a squared. This would be minus the square root of ab. This would be plus the square root of ab. And this would be minus the square root of b squared. These two cancel out. The square root of a squared is a. The square root of b squared is b. So I end up with a minus b. Notice, no more radicals. And that's the beautiful part of conjugates. They get rid of radicals in the denominator that are binomials instead of just monomials. Okay, so what you do, oh, they just did what I did, and a lot longer. All right, so when you multiply conjugates, sorry, I didn't know that was all on there. That's what you do. Wow. All right, so how can we rationalize a denominator if the denominator contains two terms with one or more square roots? And the way you do it is you multiply the numerator and the denominator by the conjugate of the denominator. Here are three examples of such expressions. All right, so I've got this first one. And what I would do is, to rationalize this denominator, is I would multiply the top and the bottom by the conjugate of the bottom. The conjugate of 5 plus the square root of 3 is 5 minus the square root of 3. And I do it on top and bottom. And we'll simplify them here in a minute. But right now, I'm just going to show you what to do. Then we'll actually do it. Okay, here I've got a radical in the denominator, so I'm going to have to rationalize, which means I'm going to multiply the top and the bottom by the conjugate of the bottom. And all you do is change the sign in the middle. Don't touch the front sign or anything else. So it's going to be 3 square roots of 2 plus 4. And my little third example here, ew, this would not be fun, but I would have to multiply the top and the bottom by the conjugate of the bottom, which you would just change that sign in the middle. All right, so let's actually do a couple of these. They want me to rationalize the denominator. Well, that means get rid of the radical, which means I need to multiply by the conjugate, which would be 5 minus the square root of 3. If I do it to the bottom, I have to do it to the top. So on top, I'm going to have 7 times 5 is 35, and 7 times the negative square root of 3 is negative 7 square roots of 3. And I can't do anything, simplify it, so the top is done. On the bottom, I have my conjugates. 5 plus the square root of 3, 5 minus the square root of 3. 5 times 5 is 25. 5 times the negative square root of 3 is negative 5 square roots of 3. Positive square root of 3 times 5 is positive 5 square roots of 3. And a positive square root of 3 times the negative square root of 3 is a negative square root of 9. And again, I'll write it out for a while, but eventually, if you know you are multiplying conjugates, don't do the two middle terms. They're always, if they're conjugates, these will always, 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 always cancel out if they're conjugates. And then what I have is 25 minus 3, because the square root of 9 is 3, and that gives me 22. So my denominator is 22. And I'm done. Okay, over here, I'm going to have to multiply the top and the bottom by the conjugate of the bottom, which is going to be the square root of 3 plus the square root of 5. Square root of 3 plus square root of 5. So on top, I have 8 times the square root of 3 plus 8 times the square root of 5. On bottom, I have the square root of 3 times the square root of 3, square root of 9. Square root of 3 times square root of 5 is positive square root of 15. Negative square root of 5 times positive square root of 3 is negative square root of 15. And a negative square root of 5 times a positive square root of 5 is negative square root of 5 squared. Again, cancel the two middle terms. So I have the square root of 9, which is 3, minus the square root of 5 squared is 5, which gives me negative 2. Now, technically I'm done, but two things. One, they don't ever like the negative on the bottom, so they put it in the middle. Two, I can reduce, and these 2's, by 2 goes into 8 4 times, goes into 8 4 times. But so what's left, and remember now that I'm putting the negative up, I got to distribute that. So that's going to be negative 4 square roots of 3 minus 4 square roots of 5. No more, actually no more denominator at all because it divided out. Alright, so you try this one, hit pause, come back when you're ready. And hopefully you got number 1. So to rationalize this denominator, I'm going to multiply the top and the bottom by the conjugate of the bottom, which will be 5 plus the square root of 10. On top, I'm going to distribute the 2. That's going to give me 10 plus 2 square roots of 10. On bottom, 5 times 5 is 25. Again, that's going to be a positive 5 square roots of 10. That's going to be a negative 5 square roots of 10, which cancel out. And there you're going to get negative square root of 100. So I have 25 minus the square root of 100 is 10. 25 minus 10 is 15. Okay. Try this one. Hit pause. Come back when you're ready. And hopefully you got 2. Alright, rationalize. I got to multiply the top and the bottom by the conjugate of the bottom, which is going to be the square root of 6 minus the square root of 13. Bottom and top. On top, if I distribute, I get 7 square roots of 6 minus 7 square roots of 13. And no, I can't subtract them, even though the coefficients match. The radicands have to match. They don't, so I'm done. Okay, bottom. I got square root of 6 times square root of 6 is square root of 36, or 6 squared, however you want to think of it. And square root of 6 times a negative square root of 13 is a negative square root of 78. This is going to be a positive square root of 78, and that is going to be negative square root of 169, or 13 squared. Middles cancel, I knew they would. Square root of 36 is 6, square root of 169 is 13, 6 minus 13 is negative 7. And simplify all the 7's, and I get a negative 1 square root of 6 minus 1 square root plus 1 square root of 13. Because a negative divided by a negative is a positive. And then they wrote it with the negative 1 at the back. Alright, so again, when do you need to rationalize a denominator? Anytime that there is a radical in the denominator. How do you rationalize a denominator? You multiply top and bottom by conjugate of bottom, or denominator. Alright. Give just a second again. Alright, I'm back. Okay, so definition of the principal nth root of a real number. What if this isn't a 2? Okay, well, it doesn't matter. If the index is even and a is non-negative and b is also non-negative, if n is odd, a and b can be any real number. Okay? So what that says is the cube root of 64 is 4 because 4 cubed is 64. If we do it my way, if I break 64 down, by 2 is 32, by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2. The only difference now is we need a bundle of 3 to make a perfect cube. Okay, before we were making perfect squares, so we needed 2 of the same thing. Now I need perfect cubes, which means I need 3 of the same thing. There's 3 2's, which is 8. The cube root of 8 is 2. Or you could think of it as the cube root of 2 cubed is 2. There's another 3 2's, which makes a perfect cube, and the cube root of 2 cubed would be 2. So my answer would be 2 times 2, which is 4. Okay? If this is odd and this is negative, your answer is negative. If this is even and this is negative, your answer is it doesn't exist. It's not, well, it exists, but it's not real. All right? So what you do is you break down 32. By 2 is 16. By 2 is 8. By 2 is 4. By 2 is 2. All right? And I'm looking for a 5th root. So now it's going to take a bundle of 5 to make a perfect 5th root. There's 1, 2, 3, 4, 5 2's there. That would be the 5th root of 2 to the 5th, which is just 2. But that's negative, that's odd, so my 2 is negative. Okay? And then just remember, if n is odd, the nth root of a to the n is just a. If it's even, then you've got to put the bars around it. All right? So here it's odd. The cube root of negative 2 cubed is just negative 2. Here it's even. When they cancel, again, it's going to be absolute value. And then it's 2. And the product rule and the quotient rule still works even if that is not a 2. All right, so let's practice some of these. We want the cube root of 24. So if I break down 24, by 2 is 12, by 2 is 6, by 2 is 3. I need bundles of 3 to make a perfect cube. There's 3 2's. The cube root of 2 cubed is 2. This doesn't have 3 of them, so it has to stay under. So I've got an outie 2 and a 3 that's got to stay under the cube root. Don't forget, when that's not a 2, you have to write it. Otherwise, we have no idea. We're going to assume the index is 2, and that's not true. All right, when you're multiplying them, you can multiply first. 4th root times a 4th root is a 4th root. 8 times 4 is 32. So if I break down 32, by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2. I need 4 to make a perfect 4th root. 1, 2, 3, 4 2's. The 4th root of 2 to the 4th is 2. And that one doesn't have 3 more to go with it. So that is going to be 2 4th roots of 2. Don't forget to put the right index in. Okay. All right, on C we have a quotient. The law says that I can either divide first and then root, or do the top and the bottom separate. I'm going to do the top and the bottom separate. So on top I've got the 4th root of 81, and on bottom I've got the 4th root of 16. So if we break those down, 81 by 3 is 27, by 3 is 9, by 3 is 3. I need 4 to make a perfect 4th. That would be the 4th root of 3 to the 4th is 3. So my top is 3. My bottom, 16, by 2 is 8, by 2 is 4, by 2 is 2. 4 2's, the 4th root of 2 to the 4th is 2. So my answer is 3/2. Here they cancel and they're even, so my answer is the absolute value of negative y, which is just going to be y. Yeah? Here they cancel and I just get negative 6 because they're odd. I don't need any absolute value bars. All right, you try this one, hit pause, come back when you're ready. And hopefully you got, come on, 5. These cancel, they're even, so it's the absolute value of negative 5, which is plain old 5. Try this one, hit pause, come back when you're ready. And hopefully you got 5 times the cube root of 2. If I multiply these first, that's going to be the cube root of 250. So if I break 250 down, by 5 would be 50, by 5 would be 10, by 5 would be 2. I got 3 5s. I'm looking for a perfect cube. The cube root of 5 cubed is 5, and 2 has to stay back in. So I've got a 5 and a cube root of 2 left over. Okay? Alright, so some division ones. As long as the indexes match, you can either do the top and bottom separately, or you can put them together, divide first, and then root. And I'm going to divide first. So that's going to be the 5th root of 32 x to the 5th. 64 divided by 2 is 32. X to the 6th divided by x to the 1st is x to the 5th. So now, if I break down 32, by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2. I need 5. There's 5 there. The 5th root of 2 to the 5th is 2. And the 5th root of x to the 5th is just x. No bars because it's odd. Okay, here I can't divide, so I'm going to split it. I'm going to have the 5th root of -1, the 5th root of 32. You can put the negative up top or on bottom, but don't put it both. Any root of 1 is 1. If it's odd and it's negative, that's going to be -1. The 5th root of 32 we just figured out is 2, so my answer is -1/2. Alright, try this one. Hit pause. Come back when you're ready. And hopefully you got 1. Alright, I'm going to divide first, so I get the cube root. 112 divided by 2 is 56. X to the 6th divided by x to the 1st is x to the 5th. So now if I break that down, 56 by 2 is 28, by 2 is 14, by 2 is 7. I need perfect cubes, so I'm looking for 3 of the same thing. That's a perfect cube. Cube root of 2 cubed is 2. And he's got to go back in. So I've got 2 and a square root of 7. My variable, x to the 5th, cube root of x to the 5th, would be the same as x to the 5 divided by 3. Well, 5 divided by 3 goes 1 whole time. Take away 3, leaves 2 left over. So I've got 1x coming out, and I've got 2x squared staying in. So now my outies are 2x, and my innies are 7x squared. Alright, adding and subtracting, we can't unless the radicands match. So you're going to break them down. 16 by 2 is 8, by 2 is 4, by 2 is 2. I need perfect cubes, so 3 are the same thing. The cube root of 2 cubed is 2, and that one has to stay back in. So I've got the 5 that was already there, times the 2 that got out, times the square root of 2 had to stay in. That gives me 10 square roots of 2, cube roots. Don't see how I just did it too? We get so used to square roots, it's hard to remember when we're talking different roots. And I can't break down 2, so that's as simple as it's going to get. Now my radicals match, index and radicand. So I keep the cube root of 2, and I do 10 minus 11, which is going to be -1, cube roots of 2. Alright, so on this one, we can't add yet or subtract because the radicals don't match. So I'm going to break down 81. By 3 is 27. By 3 is 9. By 3 is 3. I need a perfect cube. Cube root of 3 cubed is 3. And that guy's going to go back in. So I've already got the 3 out there, times this 3, times my square root of 3, which gives me 9 square roots of 3. Cube roots. See? Alright, and this one I can't simplify. The 3 is prime. So now they match. I can keep the cube root of 3, and 9 minus 4 is 5. Alright, when they give you ridiculous big ones like this, All right, you're going to have to break them down. They don't do this. They're not going to give you very many of these. All right, if I break 486 down, by 2 is 243. By 3 is 81. By 3 again is 27. By 3 again is 9. By 3 again is 3. And I'm doing fourth roots, so 1, 2, 3, 4 threes makes a perfect fourth root. Fourth root of 3 to the fourth is 3. And these guys have to go back under their fourth degree root. And then B doesn't have enough variables to get out. So I've got the Audi A times my Audi 3 times the fourth root of 3, and B would be left in. Yeah? Oh, my. No. We have a 3 and a 2 left in, so that's 6B. Okay, so now if we break down this bad boy, 3, 9, 3, 6, 6. I can go by 3 is 1, 3, 1, 2, 2. Divide by 3 again is 4, 3, 7, 4. Divide by 3 again, 1, 4, 5, 8. Divide by 3 again, 486. Divide by 3 again, 162. Divide by 3 again, 54. Divide by 3 again, that's 18. Divide by 3 again, that's 6. Divide by 3 again, and that's 2. Oh, we need bundles of 4. 1, 2, 3, 4. That gives me a 3. 1, 2, 3, 4. That gives me a 3. And these guys have to go back under. So I have the 3 that's out there times the 2 3s that I got out times the fourth root of 3 times 2 is 6. And then B has to stay in. But A to the fourth, that cancels. And that's going to give me an Audi A. Actually, absolute value of A. So I would have 3A to the fourth root of 6B plus 27A times the fourth root of 6B. Now the radicals match, and I can say 3A plus 27A is 30A fourth root of 6B. Alright, you try this one, hit pause, come back when you're ready. And hopefully you got one. Alright, so I got to break this down. I got 128. By 2 is 64, by 2 is 32, by 2 is 16, by 2 is 8, by 2 is 4, by 2 is 2. I'm looking for perfect cubes. So 3 2's, cube root of 2 cubed is 2. 3 more 2's gives me the cube root of 2 cubed, which is 2. And then this guy has to stay back in. So, and the x doesn't have enough power. So I've got 2 times 2 times y, which is 4y, times the cube root of 2x. If I break down 16, by 2 is 8, by 2 is 4, by 2 is 2. 3 2's makes it out. That one stays in. And then my x has to stay in, and then my y cubed. That's going to cancel and just give me a y. And no absolute value bars. So let's see, what do I have all together now? I have a 2 and a y out. And what's left in is the square root of, I got a 2 left in and an x. Yeah? And now, cube root. And now they match. So 4y take away 2y is 2y cube roots of 2x. Alright, we are at homework, so happy homeworking, and I will see you next time.